Okay, guys, so we're going to talk about improper integrals. Now, when I say improper integrals, I want to make it clear that this doesn't mean like bad or they don't exist or whatever. It's kind of like the same thing as improper fraction, where that's just a name we give it. Like we use improper fractions probably more than anything else, right? Than like even regular fractions or what have you, mixed numbers certainly, or fraction or decimal points. So improper integrals are useful. Um, I would say, in my experience, the most common uses of them is statistics. We use them quite a bit in statistics, in fact. So let's go ahead and talk about these things. Now, first off, a reminder of the definite integral. When we are talking about the definite integral, it's sometimes used to describe areas, but the definite integral isn't really area. It's kind of the net change, where it takes negatives and positives into account. If we're talking area, it's strictly like area above the curve or between the curve or what have you. In which case that would be, assumed all to be positive. But regardless of how we think about the definite integral, either as areas or as the actual definite integral, it's always over some closed interval a to b. So unlike our derivative, which is defined over an open interval, we often talk about these things, we talk about integrals as defined over a closed interval, and also assume that f does not have some infinite discontinuity. So with that, we have the fundamental theorem of calculus, and that is the integral from a to b of f of x dx is capital F of b minus capital F of a. But what about when we want to integrate something from, over some infinite interval or with some infinite discontinuity? That's what we call the improper integral. So to give you an idea of when this is helpful, kind of the most basic and the thing that people are maybe the most familiar with would be the normal distribution, right? So at the normal distribution, this is our mean of our distribution. We have standard deviations away, but the area under this curve is 1. That's the sum total, but it goes from negative infinity to infinity. And basically we can use like our z-tables if you've taken basic statistics to find the probability of somebody being, say, less than falling under the mean, for example. Well, that would be 50% or 0.5. And traditionally, we used to teach statistics much later in math, that is, like after calc, because technically statistics is defined using our integrals. And so you have to understand integrals to understand how it's defined. However, we've since realized that people can understand statistics because it's not that hard, at least the basic level of it isn't that complicated. You just have to take for granted that we know these areas and not really ask too many questions about how we know those areas. But those areas are defined via integrals. But like, how would we know that this integral from negative infinity to positive infinity is going to be 1? Like, that seems weird because the fundamental theorem of calculus requires closed intervals and their specific numbers, right? So essentially, that's bringing up what we're going to be talking about. Now, the idea here is that essentially, we're going to go back to what we know about from either pre-calc, college algebra, or Calc 1 about limits. So let's take a look at something like this. Now, first of all, let's take a look at its graph. Okay, so this is 4x to the negative fifth, and we're looking at 2 to infinity. Now, if you notice, from 2 to infinity, this thing has a horizontal asymptote. Now, just because it has a horizontal asymptote does not mean that we'll be able to find the indefinite or the improper integral, but it is kind of one of the first steps to necessitating that. Because essentially we have two things that can happen. If we were to add up the area under this curve, in this case it is strictly area because it's all greater than 0. So that is to say, if we were to add up the area under this curve, it's either going to add to some finite number, or because this is an infinite space, right? It might just diverge, so it just goes off into the infinites. The sum of this would just go off into the infinites. And we can't really tell based on whether it has a horizontal asymptote or not, but we can tell, like, if it didn't have a horizontal asymptote, that is, if we were like looking at x squared, for example, and we were to say, oh, I want to find the sum from 2 onwards, well, clearly that would diverge because this function doesn't converge to anything. Anyway, so we want to know, well, what's the area under that? If it does exist, can we find it? And so what we do is we think about this just like we would any other definite integral. However, we're going to call this infinity t. We're just going to be like, all right, well, we don't really know how to integrate at infinity, but we do know how to integrate from 2 to some value. Let's just call that value t. That's kind of the standard for whatever reason. So we're going to go from 2 to t of f of x to the negative 5 dx. Now you'll notice in this section our integration is quite simple. That's because you've already, I mean, like if I wanted to test you on your integration rules, I wouldn't do it with this because, you know, I don't want to test multiple things at once. Okay, so if we integrate this, we raise the power to the negative 4 now. So this is x to the negative 4 and still 4 over negative 4 plus c, but because we're doing a definite integral, we don't actually need the c. I'm going to do it this one time just to show you as a reminder of why we don't. And we're going to take this from t to 2, or I should say from 2 to t, but we write the end point on top and the starting point on the bottom here. Okay, so first of all, this is 4 over negative 4. Well, that's just a negative 1. So really we're taking this thing from t to 2. Okay, so if we were going to plug this thing in, we'd go, all right, well, plug the t in. That's negative t to the negative 4. That is to say, another way of writing that would be negative 1 over t to the 4th plus c, okay, minus 2 into this thing. That would be a negative 1 over 2 to the 4th, like that, plus c. Okay, now again, the reason why we don't need this negative, or the c here, is because a positive c minus a positive, so like minus this thing, as this distributes, we have a c minus c, and it's always going to be that way. It's always going to drop off. So we have negative 1 over t to the 4th plus 1 over 2 to the 4th. Now, we have this thing, but the problem is that we're not really interested in finding at this value t. We want to know, what about what's happening at infinity? Well, essentially, all we do is we think, okay, we have this function. We're thinking, what happens to this function as the limit as t approaches infinity here? So as t approaches infinity of this function here, what do we get? And so what we have is negative 1 over infinity to the 4th, which is just infinity, over 1 over 2 to the 4th. 2 times 2 is 4, times 2 is 8, times 2 is 16, so something like that. Now, if you recall, infinity to the 4th is just infinity, and a constant divided by infinity is 0. So we end up with 0 plus 1/16, which is 1/16. This would be the sum of all of our area under this curve here. Again, area, I'm talking area because it is all positive, but the integral isn't necessarily area, but I find it easiest to think about in terms of area. So if we add up all this space under here, it actually just goes to 1/16. So even though we're taking some infinite sum, essentially, where we have an infinite number of values, they still add up to some value 1/16. That's what it's going to be. So that is our improper integral. So all we do when we integrate an improper integral is we essentially integrate it from the constant to some infinity, but instead of doing that, we treat it as a limit like we did in like pre-calc, college algebra, whatever. Okay, so that's all there is really to an improper integral. So we officially have this kind of definition, but if we can show that the integral from a to t exists for every number from a to t, then the limit from, or excuse me, the integral from a to infinity is equal to the limit as t approaches infinity of a to t. provided that this limit exists as a finite number. So again, sometimes that will end up becoming an infinite, and we would say it diverges if that's the case. So we call it divergent if not. Okay, then it's divergent. And we can do this same logic with a negative infinity. So here, if t to some value b exists for every number from t to b, then negative infinity to b will be equal to the limit as t approaches negative infinity of f of x. Okay, provided again that this limit exists as a finite number. And again, if not, we call it divergent. So we'll take a look at another one. We have the integral from 0 to infinity of e to the negative 2x. Now again, e to the negative 2x, that looks something like this. So it does have a horizontal asymptote, but as a reminder, that doesn't necessarily mean that the integral will exist or the improper integral will exist, but that's at least a good first step. So what we're doing here is we're going to take the integral from 0 to t, and we're going to find the limit as t approaches infinity of e to the negative 2x dx. Okay, now this is technically a u sub, but we really don't need u sub for e's. This is just going to be e to the negative 2x divided by negative 2. Okay. So we're taking that from t to 0. Notice I didn't write the c here because the c isn't necessary. But if you're worried about forgetting the c in other situations, then it's worth just writing the c. Who cares, right? All right, so we plug t into this and 0 into this. So let's start with t. This is the limit as t approaches infinity of e to the negative 2t over negative 2 minus our e to the negative 0 over negative 2. Okay, so if we rewrite this, this is the limit as t approaches infinity of negative 1 over 2 e to the 2t minus e to the 0 is 1, so that would be minus a negative 1/2. Okay, so e to the 2t, if we plug in infinity here, that's going to be e to the infinity. E to the infinity is infinity. 2 times infinity is infinity. 1 over infinity is 0 plus 1/2. So that is our integral. It's 1/2. All right, let's do another one. So we have 1 over x plus 4. So that means we are going to integrate this thing again from negative 2 to t of 1 over x plus 4 dx. So this would be a natural log of x plus 4. Now, this negative 2 isn't really is making sure that we don't really actually need absolute values here, because negative 2 plus 4 is positive still, so it's okay. And from t, and anything greater than negative 2 is certainly fine. The domain of this would be anything greater than negative 4. So we really don't need the absolute values, but whatever. It works itself out either way. Okay, so again, we're taking the limit as t approaches infinity of this thing. So that is to say, natural log of t, I'm dropping the absolute values because they're not necessary, as mentioned, minus the natural log of negative 2 plus 4. Okay, so this is the limit as t approaches infinity. Now, negative 2 plus 4, that's just going to be minus natural log of 2. That's a value. Here, natural log of infinity plus 4 is going to be natural log of infinity minus natural log of 2. Now, natural log of infinity, even though logs grow very, very slowly, they still do not have some horizontal asymptote. So like if we take a look at log, okay, natural log is that it grows very quickly initially, but then it really starts to drop off. That's what we refer to as logarithmic growth. And so, but it still keeps increasing. It just increases a little less every time. And so it has no horizontal asymptote. So this thing diverges. So this thing goes off into the infinites. And so this would be infinity here. So that would be divergent. So this does not converge, it diverges. So we cannot find this integral. All right, let's do another one. So now we have from negative infinity to 0. Okay, well, um, that would be from t to 0 of x over x squared plus 1 cubed dx. Now, this is a simple u sub. We have x squared, and that's an x. So if we choose u to be x squared plus 1, then du is going to be 2x dx. So all we have to do is put a 2 in and pull a 1/2 out. So we have 1/2 times the integral. Now, when we change the boundaries, we have to keep that in mind that like until we turn it back into x's, we can't really trust these values. But we could change these values based on this relationship because like our x's are our t's here. So it'd be like t squared plus 1 here. And this would be 1 if we wanted. But it's kind of whatever. I find it just as easy to just go back to it and it avoids any potential mistakes. So anyway, so 2x dx is our du. And we have 1 over u cubed, which is another way of saying u to the negative 3. So again, I'm not thinking about the bounds of integration until I convert it back into x's. Okay, so this is going to be u to the negative 2 over negative 2 times 1/2 plus c, but again, it's not necessary. We're not going to do anything on the boundaries yet, so this is just going to be u to the negative 2 over negative 4, which is to say 1 over negative 4 u squared. Okay. Now we're going to replace our u back with what we have. So this is 1 over negative 4 times x squared plus 1 squared. And now we're going to integrate it from 0 and t here. Okay, so I'm going back to these now. Again, our u is x squared plus 1. Okay, so just a quick, well, we'll come back to it and I'll show it without like reverting back to x, just so that we can check to see if it's the same thing. Okay, so we're going to plug in our 0, but again, keep in mind that we're taking the limit as t approaches negative infinity here. So plugging in 0, we have 1 over negative 4 times 0 squared plus 1 is 1 squared minus 1 over negative 4 times negative infinity squared is infinity plus 1 squared. So that is to say, we end up with 1 over negative 4 minus 1 over infinity. Technically, it's negative infinity there. Negative and negative makes it positive, but it doesn't really matter because this right here is 0. So it's negative 1/4. Okay, now let me point out something really quick. If we had changed this bounds of integration here, so what that looks like is when we change a value from x's into u's on a definite integral, then we use the same restriction, like the same conversion here. We know that u is x squared plus 1. Okay. Now again, we had the original in terms of x was from t to 0. Okay, so essentially we're going to use this conversion of x's into u's to get this new boundary. So with t squared plus 1 is just that, t squared plus 1. With 0, it's 0 squared plus 1 or 1. So if we want to leave it in terms of u, we would integrate from t squared plus 1 to 1 and take t as t approaches infinity. So this would be again, u to the negative 2 over negative 4 from 1, and this is a t squared plus 1. Okay, so that is to say we would be taking negative 1 over 4 times u squared from 1 and our t squared plus 1. So 1 plugged into here, that's negative 1 over 4 times 1 squared, okay, minus 1 over negative 4 times t squared plus 1 squared. And we're taking the limit as t approaches negative infinity. Okay, negative infinity squared is infinity plus 1. Notice we're back to where we had this exact same thing here. Okay, so this thing here is the same as this. It's just that I didn't have to convert back to x's if I changed my bounds of integration. So that's always an option, and I find that the textbook will do that more often than not, if not always. I kind of go back and forth. I don't really bother converting these over if it's not very hard to switch back into x's. But in the case of our inverse trig substitutions, where we go from like x to theta to u to theta to x, it's probably worthwhile for me to just change my bounds of integration because it just makes my life about a million times easier then. All right. Okay, so what about when we have something that's like a negative infinity to a positive infinity? Okay, so again, in the case of the normal distribution, and let's see the equation of this thing, okay? Sigma here, that's standard deviation. Mu is our mean. So it's this function here where we're looking for x. So it's similar, sort of, okay? But basically we're just looking for some infinite sum now. So this here is x e to the negative x squared. Okay. Let's take a look at what that looks like. All right, now first of all, what do we expect this integral from negative infinity to positive infinity to be? Well, if you notice, this and this are basically the same functions, just mirrors of each other. So this will be a negative of whatever this is most likely, so I would assume that the integral should be 0. But let's see. Now, what we do when we have multiple infinities here is we basically have to break it up into two things. And it doesn't actually matter how we break this thing up. So if we take a look here, I can break this up at any point, but I think 0 is probably going to be my easiest place to break it. But if I take the integral from negative infinity to 0, and then take the integral from 0 to infinity and add them together, I will get my overall integral. So that's what we have to do, is we have to break it up into 2 points. And again, it doesn't matter where we break it up. We just have to break it up somewhere. I generally will break it up somewhere easy, like 0, but it's whatever. So essentially, this thing from negative infinity to infinity is going to be equal to the integral from negative infinity to 0 plus the integral from 0 to infinity. You might say, oh, but we're adding 0, like the spot is 0 twice. Well, yeah, but what's the sum at any point in a function? Like if we think the area of a line at any point, a line has no area. So one spot being added twice, that's adding 0 twice, it doesn't matter. And it might seem a little counterintuitive when you think, oh, but aren't we adding up a bunch of zeros and somehow getting value? Well, yes, we are. But that's the joys of infinites. But when we have some finite spot, that's a line, the area of a finite line is nothing, but the area of an infinite number of lines starts to add up to something. So that's all we're doing, is we're just taking this integral. So essentially we just have to do it twice. So first of all, let's go ahead and just find the integral, x e to the negative x squared dx. Well, u is going to be negative x squared. Du is going to be negative 2x dx. So we have an x and a dx. I need a negative 2 in here. I'm going to pull out negative 1/2 here. So that's negative 1/2 times the integral. Negative 2x dx becomes du. E to the negative x squared is just e to the u. Terrible e, but whatever. Okay, integral of e to the u, it's e to the u. Plus c, technically. And then we replace the u's back with what we said. That was a negative x squared for u. So that is negative e to the negative x squared over 2 plus c. This is our f of x. So all we have to do then for our integration is to take the limit as t approaches negative infinity of our negative e to the negative x squared over 2 from t to 0. And then we're going to add it to the same thing, the limit as t approaches positive infinity now of negative e to the negative x squared over 2 from 0 to t. So we're just doing definite integral twice. Okay, so let's go ahead and take a look at this. 0, okay, that's negative e to the 0 over 2 minus negative e to the negative infinity squared over 2. Okay, keep in mind that this thing is being squared first. When the square happens first before this. So that is to say, that is negative 1 over 2 plus 1 over 2e to the infinity squared. Again, this thing here, that's just 0. So we have negative 1/2 plus 0. Now let's take a look at this one, plugging in our t and plugging in infinity for it. We have negative e to the negative infinity squared over 2 minus 0 plugged in here is going to give us negative e to the negative 0 over 2. So that's going to be a same thing here. Bring that to the bottom. That's a 0 plus 1 over 2. So this one is 1/2. This one's 1/2, but it's a negative 1/2. So negative 1/2 plus 1/2 gives us 0. So the integral from negative infinity to positive infinity is 0. If we were talking area between the curve, the area between the curve would be 1 because this would be a area, so it would be 1/2, and this would be 1/2 for a sum total of 1. So technically speaking, this could be a stand-in for some kind of probability if we just made it absolute. That wouldn't do it. Anyway. Maybe if I did the absolute here, yeah, like that, then, I mean, if we had some distribution like this, where we have like 2 means and kind of goes down to 0 here, that'd be a weird distribution, but, you know, it would work for probabilities. Okay. I guess we could do it, think about it like a book, right? The probability of being on, you know, to the left of a certain margin in the book, since we're kind of looking at some book that's open on its spine. Who knows? Whatever. Anyway. So that is how we deal with a negative infinity to an infinity. Nothing special, just kind of break it up. All right, now let's talk about another thing. What about when we have some, well, I guess this is the definition continued from our first, and this is just defining for our negative infinity to infinity. And that is, if we want to find negative infinity to infinity, first of all, the a to b and negative infinity to b here are convergent. Then we can define this. The only thing I should note is actually, this is a typo here. They need to both go to the same point. Maybe I should make them both a, since that would make the most sense. Okay, then this is the integral from negative infinity to a, and from a to infinity. Okay. All right, but anyway, that's just defining that. Okay, let's do another one just to see it again. So again, this thing here, it doesn't matter where we split it up. It really doesn't. But I usually like to split it up somewhere that makes sense. Okay, so here, I'm going to split it up as 0 again, just because 0 is easy. And also it's a nice symmetry around that. Not that it really matters. But the benefit of that, technically speaking, is if we were to just integrate like one side, Well, the other side is a mirror of it, so technically I could just double it then. So that would be the benefit of splitting it at 0. But anyway, so first of all, let's integrate this thing. This is the integral of 1 over 1 plus x squared. Okay, now if we recall on our table, let's see, books, table of integrals, this thing here is like a squared plus x squared. So this is almost certainly some table, so we don't really have to, I don't know, bother with it. Let's see. These are those things. Let's see. Surely I could find one on it. I feel like this is definitely something that we have. Oh, right there. Tan inverse. I don't know why I was looking elsewhere. I think I caught here looking at the negative and I was like, I thought tan inverse. Anyway, whatever. Tangent inverse. Okay. So this is just going to be tangent inverse. Let's just pull that up. Okay, 1 over a, so that's 1 over 1 of x over 1, so it's tangent inverse x plus c. Okay, nice and simple, that one. Okay, and we want to take it from negative infinity to infinity. And again, what we have to do then is we have to break it up. So tangent inverse of x from, we're going to go from negative infinity to 0 plus tangent inverse of x from 0 to infinity. And this is all the limit as, well, I guess we can replace these infinities with t's so that we can officially do the limit, t to t. I mean, you know, at a certain point, we recognize that that just writing it as the infinites is fine too, since we're going to plug them in eventually anyway. Anyway, so if we take a look at this thing, let's first look at what tangent inverse is. Tangent inverse of x, okay? All right, so if we look at this thing here, like what is the horizontal asymptote of this thing? Like what is this thing going towards if it has one? So if we plug in like tangent inverse of some really big number, let's say like some insano number, notice we're going towards some value. Now what is that value? You know, you might want to try, no, not quite right. Pi halves. So it actually has this thing here, this horizontal asymptote, and that is when y equals pi halves, okay, and negative pi halves. So that is the horizontal asymptote. Essentially, that's what it becomes as it goes out to the infinites. Now, how do we know that? Well, one, I know that because I can usually, if I see an irrational number, I'm usually okay as long as it's one of our special ones like pi halves, pi thirds. I can usually get it. But let's describe why that actually is. Tan inverse is the inverse function to tangent of x, and tangent of x has some, I wonder, okay, it has essentially asymptotes every time, because if you remember, tangent is sine of x over cosine of x, right? So essentially it has an issue every time cosine of x is 0, but we're basically just looking at a single one, not every single one. So it's from when cosine is 0 here to cosine is 0 here. So let's take a look at when cosine of x is 0. So it's at negative pi halves to pi halves. That's when it hits 0. And so that's where our vertical asymptotes are for tangent. And so tangent inverse the vertical asymptotes become horizontal asymptotes, so that's really why. But anyway, so we end up with that. Let's go ahead and write that out. Again, we have tangent inverse of negative t. I just did a negative t for this infinity just because like then I could just have overall a limit. I could have did t negative infinity, t infinity, whatever. Minus tangent of, oh, I'm sorry. We actually have the top one caught up. Tangent inverse of 0 minus tangent inverse of negative t plus tangent inverse of t minus tangent inverse of 0. Okay, now, if you're not sure, again, tangent inverse here, tangent inverse of 0 is 0. Okay, so that's going to be a 0 minus tangent inverse of negative t as it goes to infinity. That's going to just be, again, let's take a look at this thing. Tangent inverse has a horizontal asymptote of negative pi halves, so that's negative pi halves. Plus tangent inverse of infinity, which again, oops, tangent inverse of infinity is the positive one now, so that would be positive pi halves is what it's going towards, minus tangent inverse of 0, which is 0. So that's a positive pi halves plus pi halves, pi. So the total sum of the area under the curve there would be pi. Now, again, notice that the left-hand one and the right-hand sum are the same. Adding them up is just doubling it. So as mentioned, if we had originally taken this and just gone, oh, who cares? Let's just find the left-hand side and then double it. That's hoping that it's a nice mirror. It is a nice mirror, but that's maybe putting a little bit of trust in it. But you could have in this case. But it's better safe than sorry, right? Just to do the whole thing. Okay. Now, let's talk about some other things. Now, let's take a look at something like this. The integral from 0 to 5, 1 over the cubed root 5 minus x dx. Okay, so this doesn't seem problematic like the other ones. So in the previous problems, we've been going to infinities. So this doesn't seem like it should be problematic. But let's take a look at the graph. So if we have 1 over 5 minus x to the 1/3, we see that basically we have no issue at 0, that's not a problem, but as we go to 5, we get a vertical asymptote. So this thing goes off into the infinites as we approach 5 from the left. It goes to positive infinity. It doesn't matter for our case, but since our interval is from 0 to 5, but if we were coming in from the right, it goes to negative infinity. That's the sign of a vertical asymptote here. So this is problematic because at 5, our function doesn't exist. So what do we do in this case? Well, we basically do the same concept that we did in our previous ones, but now we're going to approach 5 as a limit from the left-hand side. Since we're approaching from the left, we're going to approach from the left here. So we are going to take the limit as t approaches 5 from the left of this integral from 0 to t of 1 over the 3rd root 5 minus x dx. So we're going to take this integral first. We first need to integrate this thing. So let's take a look at that. I'm going to write this as 5 minus x to the negative 1/3. This is what I'm going to integrate. And I'm going to drop these for now just to save myself the hassle. So let me start by doing an indefinite integral on this thing. So we can use u sub if we want. We can also do this without u sub, but just for your reference, our u would be 5 minus x. So that would mean du would be negative dx. So that's why we don't really need it, is like a negative and a negative. Anyway, so the negative in the dx becomes a du. This becomes u to the negative 1/3, something like that. Okay, so the integral of this u to the negative third is going to be u to the 2/3 divided by 2/3, and we have that negative here, plus c. So that is to say negative 5 minus x to the 2/3 times 3/2, so I'm going to write that 3/2 like that, plus c. Now, we don't really need the c because we're going to do a definite integral, but I at least have it just out of habit. Okay, so what we want to do is we want to take this from t, 0 here, and we want to take the limit as t approaches 5 from the left-hand side and see whether this thing converges to something or not. Okay, so plugging in our t, I mean, it's the same as doing the x. We could just call it from x, but we'll do it from t. So we have negative 3/2, 5 minus t to the 2/3, plus c minus the 0 into here. We get negative 3/2 times 5 to the 2/3, plus c. And so our c's, of course, cancel. We're taking the limit as t approaches 5 from the left-hand side. Okay. So, as t approaches 5 from the left-hand side, I mean, we can just throw 5 into this thing. 5 minus 5 is 0, so this becomes 0 minus, well, this is actually a plus here, plus 3/2, 5 to the 2/3, and that is canceled. So we end up with this quantity. So let me clean this up just a little bit. So 5 to the 2/3 divided by, or times 3/2. See if it cleans up a little bit. It might not. It's okay if it doesn't, but it's worth trying out. Nope, it doesn't. So I guess we're just going to leave it there. I guess that makes sense. So we get this 3/2, 5 to the 2/3. Now we can potentially try and check this out as like an approximation, if nothing else. So, if we integrate this thing, functions, since it's kind of it's definite integral, it's just an improper one. I just want to point out that if we plug in 5, 1 over 5 minus x, to the 1/3 dx, we will get the same value here. So notice that Desmos can actually do improper integrals as well, within reason. I don't know if it can do all of the improper integrals, but it generally works. Okay. Let's now talk about this in kind of a definitive definition here. If f is continuous on some interval from a to b, but notice not including b, and is discontinuous at b, something that happened in our previous problem, then the integral from a to b of f of x dx is equal to the limit as t approaches b from the left-hand side of the integral a to t f of x dx, if the limit exists as a finite number. That's something we just got done doing. In reverse, if we have something that starts at a discontinuous moment at a here, then we just do the opposite. We're approaching it from the right-hand side, from t to b. And if f has a discontinuity at c where a is less than c, which is less than b, and both the integral from a to c and the integral from c to b are convergent, then the integral from a to b of f of x dx is equal to the integral from a to c plus c to b. So if we have like a disconnect somewhere in the middle, we just split it up around that middle and take two improper integrals. That's the point of this. And essentially we're going to apply both of these in here to find those integrals. That's all this is saying. Okay, let's take a look at another one. Okay, so we have the integral from -2 to 14 of dx over the fourth root x plus 2. Now, I think we can tell that negative 2 is going to be a problem here. Negative 2 plus 2 is 0. Fourth root of 0 is 0. 1 divided by 0 is undefined. But we'll go ahead and graph it too, just so you can see this. So let me hide that. We have 1 over x plus 2 to the 1/4. Okay, so as mentioned, here we have some issue at negative 2. And notice our function actually doesn't even exist past this negative 2. So anything past it no longer works because it's the fourth root, and those would then be negative, and an even root of a negative is on the complex number line. Okay, so we can only approach this thing from the right-hand side. So we're looking at it from negative 2 to 14, or specifically, kind of like 14 to negative 2 from the right-hand side is another way to think about it. So let's start by integrating it, but basically what we want to do is we want to take the integral, the limit, as t approaches negative 2 from the right, t 14 here, dx over the fourth root x plus 2. Okay, so this is what we want to integrate, and again, I tend to just start with my indefinite integral. So I'm going to integrate this thing. It's going to be x plus 2 to the negative 1/4 dx. Now again, we can use u sub where u is x plus 2, but that is very unnecessary. I did it on the previous one, even though it was kind of unnecessary, just to make sure there was no confusion. But on this one, I'm just going to skip that. We're going to integrate this. This is going to be x plus 2 to the, we're adding 1, so that's going to be to the 3/4. And we're going to divide by 3/4 or multiply by 4/3. And then we divide by the derivative of this inside here. The derivative of this inside is just 1, so we don't need to worry about it. Okay, so this is our indefinite integral. We're going to take the limit as t approaches 2 from the right-hand side, or negative 2, excuse me, negative 2. Remember right? Yes, negative 2 from the right-hand side. Integral t to 14 of this thing. So really, I guess I didn't need to write this again. Let me just move this up here. So we're going to take this from 14 to t like this. Okay, so let's plug in our 14 here. So again, we're going to plug in our upper bound here. 14 plus 2 is going to be 16. We have 4/3 times 16 to the 3/4 plus c, but the c's are going to drop, so I'll draw it anyway. Minus our t plugged in here. In this case, we have t plus 2 to the 3/4, okay, plus c. All right, and we're going to take the limit as t approaches negative 2 from the right-hand side. Okay, so obviously these c's cancel. Negative 2, if we plug it in here, negative 2 plus 2 is 0. This becomes 0. And we're just left with 4/3 times 16 to the 3/4. Okay, so let's go ahead and check that out. We have 4/3. Oops, on Desmos, there we go, 4/3, 16 to the 3/4, which is 32 over 3. Might as well get that in exact terms. Now let's compare that to the integral here. The integral from negative 2 to 14 of 1 over x plus 2, 1/4, 1/4 dx. All right. So if you look, those two agree with each other. Okay, cool. So that checks out. All right. Let's take a look at another one. So we have the integral from 0 to 6 of 1 over cube root 5 minus x. Now this should be familiar. We've already done this. But notice in our first one, we did from 0 to 5. 5 was problematic. But now we're going from 0 to 6. So we're passing over the problematic point. Let's take a look at this thing. So if we have something like 1 over the cube root of 5 minus x, okay, and we're taking this from 0 to 6, then we're essentially breaking this at 5. We have a discontinuity. Now, another thing to note is we're talking about, in this case, the definite integral. If we were instead talking about the area, that would be different because this portion of it is below the x-axis. So this is a negative, this is a positive. The definite integral will take some of the positive and some of that negative, so it will be a little less than what we saw in our previous problem, or on our first problem of this sort. It's going to be less because this portion is going to be a negative. But if we're talking about area, it would be more. If we'd have to think about this term in absolutes. But we're just talking about the definite integral. Okay, so the idea here is that we need to break this up from 0 to 5, and then we need to take it from 5 to 6 and take its integral. So essentially, what we want to do is say, okay, well, f of x is equal to squiggly brackets, 0 less than or equal to x less than or equal to 5 of this thing. So we're going to take this portion of it, and then we're going to take the portion from 5 to 6. So we're going to take a look at this portion here and find its area. So we need to break them up into 2 points is the point here. So we are going to, this thing here is going to be equal to the integral from 0 to 5, 1 over the third root of 5 minus x dx, plus the integral from 5 to 6, 1 over the third root 5 minus x dx. Okay, now we've already done this portion. We just need to do this portion. So we'll pull from the other. The other thing I want to note is that if we were talking about area, then we would want to take it and either do it in terms of absolute, or because it's going to be negative, or we take it from 6 to 5 like this. We just flip the bounds of integration, and that will force it to be positive as well. But we're not talking about area, we're just talking about definite integral. Okay, so we have this portion, we've already done that. Let's go ahead and pull that one. Not that one, this one, okay. So we already know the first half, this portion. And again, how did we get this portion? Well, this came from our improper integral. So now we're going to take this thing plus the integral from 5 to 6, 1 over third root 5 minus x dx. Now we've already integrated this thing, so I'm just going to go ahead and pull it again. So as a reminder, this is our integral. So let's go ahead and copy this. All right. So we end up with the limit as t approaches 5. In this case, we're taking it from the right-hand side of this thing from 6 to 5. And we're going to add it to this 3 over 2, 5 to the 2/3 that we got in our first half. Okay, so if we plug in 6, we get 6 into here. We have negative 3 halves times 6 minus x, which is going to be, 5 minus 6, which is going to be negative 1 to the 2/3, which is going to be a positive because it's squared first, so that's positive. Plus c minus, if we plug in 5, but we're actually not doing 5. As a reminder, we're doing t, so that's my bad there. So, and then taking the limit, we have negative 3 halves t, 5 minus t to the 2/3 plus c. Okay, so this is the limit as t approaches 5 from the right-hand side. Doesn't affect this one, but it does affect this one. This would make this 0. These c's cancel. And we have a positive times a negative, so that's going to be a negative as we expected, since it's below the x-axis. So we have minus 3 over 2. Okay, so if we take a look at this thing, they both have a 3 over 2, so we could technically factor out a 3 over 2, but it wouldn't really make that look any better, so I'm not going to bother. Okay, so let's find what that point is. So we have 3, oops, not here, oops, okay, 3 over 2 times our 5 to the 2/3 minus 3 over 2. Okay, so it's 2.8 something. So let's go ahead and compare that to the integral, because our integration on Desmos can also go across these. So it can handle this from 0 to 6 of our 1 over 5 minus x to the 1/3 dx. And you see that we get the same value. As mentioned, if we were talking about area, we'd add 3/2 instead of minusing 3/2. So if we were talking about the area between the curve, we would be adding this portion and that portion together as absolutes. Anyway, so that checks out. So again, the point is when we have it over some break, you just break it up into 2. Now, sometimes those will diverge, but if it converges, we can at least do that. Okay. Now, let's go ahead and talk about convergence and divergence when maybe we can't really figure out whether, like we can't integrate it and find indefinitive terms of an actual value. So, we have this thing called the comparison theorem. And to be honest, it's kind of similar to kind of the squeeze theorem as concept. But basically, we use this comparison theorem to help us determine whether things converge or diverge. And we actually use these later on in the class when we start talking about series and sums. Well, series or sums, they're just infinite sums. Anyway, when we start talking about series, and so we actually use the same basic concept. So suppose that f and g are continuous functions with f of x greater than or equal to g of x, which is greater than or equal to 0 for x greater than or equal to a. So that is, after some point, doesn't really matter where that point is. We sometimes call it starting at 0, but it doesn't have to start at 0. It just needs to start at some value. So after some point, our f function is always greater than or equal to our g function. That's the point here. Then, if we can show that our integral from a to infinity of f of x is convergent, so as we go out, if we can show that this f function is convergent, then by comparison, g must be convergent as well because it's less than f. So f is convergent, and so anything less than f should also be convergent as long as it's greater than 0. So we are squeezing g essentially in between our x-axis and our f function and showing that because f converges, then anything in between 0 and f must also converge. By that same logic, if we show that g here is divergent, then our f function must also be divergent because it's greater than it. So if something's diverging and it's less than something else, then clearly this must also diverge. Okay, so again, this comes back up when we start talking about our series and showing convergency of series. And being able to recognize whether something converges or diverges is actually very important because if we know something converges, then we know we can, potentially waste time trying to find what it converges to. And if we can't find exactly what it converges to, we can at least approximate what it converges to. But if we know it diverges, we know not to waste our time trying to approximate or find the definite convergence there. So that's actually a pretty useful thing for us. And as mentioned, we use it a lot when we start talking about series. So let's go ahead and take a look at how we use this. Okay, show that the integral from 0 to infinity of e to the negative x squared dx is convergent. Now, e to the negative x squared is a classic integral in which there is no elementary equation that can describe its integral. We cannot describe this thing's integral in terms of like functions that we know how to describe, like rationals, exponentials, logarithmic, quadratic, or any polynomial for that matter, those kind of things, or some combination of them. This just straight up doesn't exist in one of those forms. However, it it does exist, like the integral of this thing does exist. So let's go ahead and take a look at this thing. So first of all, we'll take a look at the picture of it, or the graph. E to the negative x squared. All right, so if you notice, this is actually a pretty nice little graph. It looks essentially like a normal distribution. We have a nice bell curve here. Okay, so it's really not a problematic function overall. Like the function itself isn't a problem. It's just the integral is the problem. So in order to show that this thing would converge, we'd have to be able to integrate it normally. But we can't integrate this. So instead, we have to find some other function that works better. So let's do one similar to it that we can actually do. Let's try like e to the negative x. Okay, so e to the negative x is going to work for us. This is something we can integrate, and also, while e to the negative x is less than our e to the negative x squared, so this black one here that we just created is actually less than our function from 0 to 1, it doesn't really matter because it's greater than our function off into the infinites. So this will work just fine. Okay, so let me go ahead and snip this real fast, just so we have it on our graph here. Okay, so basically, in black here, we have our e to the negative x, and in purple, we have our e to the negative x squared. So, as mentioned in our previous thing, all we have to show is that, well, this thing here is greater than this one after some point. So that is to say, e to the negative x is greater than or equal to e to the negative x squared from x greater than or equal to 1. Basically, from this point onwards, it's fine. So all we have to show then is that the integral from 1 to infinity of e to the negative x dx converges. Now, why is it that we don't really have to worry about it converging from here to here? Well, this is a definite integral from 0 to 1. It's not an improper integral. This area clearly exists. It is something less than 1. The area between the curve of the purple is less than 1. It's also less than 1, and less than the purple one in this block here, but we don't care about that. The integral of e to the negative x squared from 0 to 1, we definitely know it converges to a value. It's less than 1. This is a finite number. In fact, we could even, do it on Desmos if we really wanted to. So let's go ahead and show that real fast. So the integral from 0 to 1, hopefully this one works. I know it's not an elementary integral, but I think Desmos doesn't actually integrate it. Yes, there we go. So it's less than 1. I was going to say, Desmos most likely doesn't find the integral via like tables in this case. What it basically does is actually approximates it to a certain point, which is something we learn later on when we start talking about series and things like that. Okay, so it's 0.746. Okay, so again, it's less than 1. It converges. So we don't have to worry about this. This portion converges. All we have to show is that this portion converges. And so we only need to show that our function that's greater than it converges. So let's go ahead and see if it converges. This integral would be the limit as t approaches infinity of the integral from 1 to t e to the negative x dx. This is what we need to show. So the integral of e to the negative x is going to be e to the negative x times negative 1, or divided by negative 1 more accurately, but whatever. So we have this thing plus c, again, force habit, t, 1, and we have the limit as t approaches infinity. Okay, so plugging this in, we have negative e to the negative t plus c minus, now plugging in 1, negative e to the negative 1 plus c. So these cancel, obviously. We have negative 1 over e to the infinity, because we're taking the limit as t approaches infinity. Negative 1 over e to the infinity plus 1 over e. Now, e to the negative infinity goes to infinity. Negative 1 over infinity is 0 plus 1 over e. So it converges to a value. So what we say then is that since our e to the negative x from 1 to infinity converges, and e to the negative x is greater than or equal to e to the negative x squared on the interval when x is greater than or equal to 1, then by the comparison test, e to the negative x squared also converges. So we know then that this thing must converge. We don't know what it converges to at this moment. All we know it converges. But as mentioned, we can now waste time trying to either find it in exact values or approximate it. Now this doesn't have an elementary integral, so you're probably going to have to approximate it. But you can approximate it. Alright, so that has been our improper integrals, convergency, divergent integrals, and kind of what we do. Again, it's nothing too complicated. We simply are talking about it now in terms of limits. So even though they're improper integrals, we can still integrate those things. So that's been our improper integrals. Thanks for watching.